the Astronomical Society of Edinburgh's talk this evening. In a moment, Mark will do some introductions in terms of the subject matter and our two speakers. Meanwhile, let me just go through the protocols again for our members and anybody joining us on YouTube. If members have any questions, please put them in the chat area, and as normal, Peter will go through them and ask individuals to come online at the end and ask those questions. If you're joining us on YouTube, Mark will keep an eye on the comments section. So if you want to put your questions on the YouTube comments, Mark will feed them across and probably ask them himself. So with that, if you'd all keep your microphones muted until that point in time, I'll hand over to Mark. Thank you, Mark. You need to unmute your mic, though.
My son just reminded me of that. Yes, very good. So I'm delighted to welcome Anastasia and Angelos to the Society. Thank you for doing this talk for us at fairly short notice. It's very, very kind of you. The reason I was very keen to get them to talk to us is because I've been working with the ExoClock project as well recently. I'd set myself a target last year to see if I could detect an exoplanet, not discover one, obviously. And then I discovered the ExoClock project, and it's a very exciting project that amateurs can actually get involved in what is really the leading edge of astronomy at the moment. I think the exoplanets. It's not that long ago that we didn't actually know of any exoplanets, let alone be able to see them in your own back garden as well. So with that, it'd be nice to hand over to Anastasia and Angelos, and if you can share your screen, please, that would be great. Thanks very much.
Right. So let me share the screen. Can you see my screen? Okay.
Yes, that's good. Thank you.
Perfect. Okay, so hello everyone. Many thanks, Mark, for the invitation and for your kind words. And many thanks everyone for being here. It's a pleasure for us to join this meeting, even virtually. And the talk will be about ARIEL, which is a future space mission. But before we talk about future, it's important to talk about the present and the current condition on exoplanets. So the number of exoplanets has been growing fast during the last 20 years, and this number is keep growing every day. At the moment, we have reached more than 4,000 planets. And here on the graph, you can see the distribution of these planets by the different methods. So most of the planets have been found by the transit method and also the radial velocity. The transit is with the green, and with the red is the radial velocity method. And with these different techniques, we have managed to find different types of planets. So here again on this graph, you can see 4 different categories of exoplanets that we have found so far. With the red is the radial velocity, and with the blue is the transit method. So 4 different types. On the right-hand side of the graph, you see the long period gas giant planets. And these are planets that are formed and, of course, orbiting further away from the stars. And that's why they're long period planets. And they're called also cold Jupiters. Jupiter and Saturn in our solar system belong to this category. And on the left-hand side, you see, again, gas giants, which are closer to their host stars. So that's why also they are known as hot Jupiters. On the middle of the graph, we have planets that are less massive than gas giants. So planets that are also more massive than the Earth. And these are closer to their host stars, known as warm super Earths. So It's a planet that we don't have, a planetary analog we don't have in our solar system, a super Earth. It's a planet that is smaller than Neptune, but still bigger than the Earth. And finally, planets that are very close to their host stars and they're sub-Earth or Earth-sized. Again, hot, very hot, closer to the stars. So hot sub-Earths. The really main take-home message from this graph is that we have only found planetary analogs for Jupiter-type planets, and we don't have for any other planets of our solar system analogs. And what we have found as well, we don't have it in our solar system. Gradually, by having the radius of the planets and the temperature, we can start imagining of these worlds, how they would look like. And we realized that there would be a wide variety of them, a large variety of planets with higher temperature or smaller, bigger or smaller density. But still, the information that we have is very limited. So let's take the big picture of these discoveries and what we have really realized so far from the different discoveries of exoplanets, the big number of 4,000, because we know that they're there, but the number is growing. So first of all, there are at least as many planets as stars in our galaxy. Secondly, most planets in the galaxy are super Earths, which is a planetary analog that we don't have in our solar system, as we said. Another point is that there is one Earth-like planet in the habitable zone around every red dwarf. But bear in mind that most of the stars in the galaxy are also red dwarfs. And finally, that statistically again, 1 out of 10 sun-like stars has one Earth-like planet. You may ask how we reached these conclusions. And here you have the graph of the different categories of planets, the distribution of these planets with the categories. So all the 4,000 planets are here. Apparently, you can see that most of the planets that we have found are this type of more larger planets than the Earth or smaller than the Neptune, which is the super Earths or mini Neptunes. Even among the scientific community, there is a debate about these planetary types because we don't really know if they are larger versions than the Earth, or smaller versions than Neptune, something we don't know. And also you have the hot Jupiters, which is also considerable amount of them, and we don't have it. We don't know. It's something that we don't have in our solar system. Now, again, all this information and all these discoveries are quite limited because we can know the mass about the planets from the radial velocity method. This is the one example, the curve, or the radius from the transit method. And then we can also calculate the distance between the star and the planet and find also the temperature, estimate the temperature. So far, we have found, estimated the temperature for some planets, but for a very small amount of them. And we have even characterized more from the atmospheres for a few exoplanets. So we have characterized very few atmospheres. And I will pass to Angelos, who has studied atmospheres, and this is his research field, the atmospheres of planets, and he can talk to us about his own studies.
Unmute. So for a very small number of planets, we have some insight about the atmosphere. The last decade, progress has been made mainly thanks to the Hubble Space Telescope and to the Spitzer Space Telescope, which both have given us the necessary precision to do this. So we expect that, at least for the hot giant planets, that we will find some molecules like the ones that you can see here, carbon dioxide, water, methane, monoxide, or ammonia. But we don't really know if they're there unless we observe them. So at the moment, we'll go to the next slide, please. So at the moment, we have observed mainly hot Jupiters or Neptunes, so gas giant planets. And when I say large, I mean something about a few tens of them. So around 50 exoplanets have been observed. And whenever we find an atmosphere so far, we also find water. Of course, one reason is because we are biased towards finding water. We are looking for water. We expect it to be there, and it is a molecule with a very strong signatures at the wavelengths we're looking at. So, but this is mostly for gas giants, and our knowledge about smaller Earths, smaller planets like super Earth, is quite limited. So, among the super Earths that we have analyzed so far, I'd like to highlight two of them for which I have worked on. So the first one is, go to the next slide, is 55 Cancri is a quite extreme example because it is a rocky world, but it is orbiting so close to its host star that the temperature on its surface is expected to be more than 2000 degrees. In these temperatures, we believe, and even higher. So in these temperatures, we believe that the surface of the planet is molten, so it is covered by a lava ocean. Now, interestingly enough, we were able to find a very light atmosphere around this planet, and it's still under debate where it's coming from. But one idea is that probably this gas is coming from inside the planet, so it's like outgassing or evaporating, something like this. To another interesting example, but on the other side, this is a planet called K218b. It was discovered by the Kepler spacecraft during its second mission, so K2. And it is a planet that it is in this regime of super Earths and mini Neptunes. And it's orbiting an M-dwarf star, so a cool star. But the interesting thing about this planet is that it is within the habitable zone of its star. So the estimated, and I'll say estimated, radiation that it receives is similar to the Earth. So this is a planet that we call habitable zone planets. So in this planet, we also found water, and it was the first time something like this. It was very interesting because it shows us that there are such kind of planets, like with the correct temperature as the Earth, and also having water on their atmospheres. It was only the first one because at the moment, more and more planets are being discovered, especially by the TESS spacecraft by NASA. And hopefully we will have more of these examples in a few years. So the future in general is very bright because you can see here Hubble and Spitzer, which were the first telescopes to be used, but they were not really built to do this kind of science. In the next decade, there will be many missions, some dedicated to exoplanets, some not, but like the James Webb Space Telescope, which we are waiting to fly next year. And it will do bright science about exoplanets. Of course, from the ground, there will be the extremely large telescope that will be our first window to very small worlds. And the highlight for me, for us, for the decade will be the ARIEL space mission, a dedicated one for exoplanets. And Anastasia will tell us more about ARIEL.
So, yes, the future is bright. ARIEL, in our topic now. ARIEL is a European Space Agency mission prepared for launch in 2028. It is a telescope, it will be a telescope of 1 meter, and it will carry a spectrograph to cover wavelengths between 0.5 to 7.8 micrometers, so mostly visible and infrared from the spectrum. And the main questions that is going to address are: what are exoplanets made of? How do planets form and how they evolve? And finally, what is the weather there? In order to achieve this and answer these questions, it will observe 1,000 exoplanet atmospheres. And considering that we cannot send anything to exoplanets or even travel, or as we do in our solar system, sending some probes or other orbiters, the only way and the only window we have at the moment is the atmosphere. And the atmosphere is a very powerful tool because it can tell us and give us information about different processes on the planet. from astrophysical, also to geological, and even, of course, life as we know it here on Earth. So the atmosphere is really the only path and the only way we have at the moment. Now, the main goal, most important goal for ARIEL will be to find out the chemical composition of the atmospheres of all these planets that we observe, and of course, gradually start creating what we imagine as the planetary H-R diagram. Think about the H-R diagram of the stars and the revolution that it brought when we really built it, because it's when we really understood how stars form and how they evolve. Of course, planets are much more complicated and they undergo much more complicated processes, so it's an even harder task. But it's when we imagine that we'll start placing all the different categories into this graph and diagram. I know that it seems quite complicated, but just like very briefly, we can see some examples. We have the hydrogen-helium accretion line, which is above here, and all the planets which are massive enough to gain some gas will be placed here, like Jupiter or Saturn, or the gas giants will be around here. And all the way around, all the planets that have too low mass to get any gas, they will be below the impact escape limit line. And you can think of Mercury as an example, which is very small to have an atmosphere, or also planets that are bare cores because they have lost in some case, in some way, the atmosphere. On the very right hand side of the graph, we have the surface melting line, and the temperature there is extremely high. So as Angelos mentioned about 55 Cancer, all the lava wars that we imagine will be placed around there. And in between, we have all the planets like Venus, Mars, and Earth, or the super Earths that we are observing, which is planets that we don't really know. And these planets will either be cores, mainly with mantles, or also in some case with atmospheres. And another example will be the H2O, the water runaway greenhouse line, which is again on the right of the graph. Other planets like Venus, for example, will be there. They have very high temperature, so any water will not be able to be maintained in the surface. Very briefly, of course, this is very complicated and is kind of what we start imagining as the diagram, but only with a population study like ARIEL, we will really know what is going on. The second main objective of ARIEL is to understand how these planets ended up to their current state. So finding out the planet history. This is even more complicated, but we can take an example. For example, think about every planet. It starts from very small rocks, the planetesimals, as here on the graph. And when they come together, they form the planetary embryos, which is a very protoplanet, the first stage. If the formation stops here, very simply, we end up with a planet, a terrestrial planet, like Mars, as you see on the top. But if accretion continues, then the planet can either be an Earth-type planet, as you see here, or if the planet is massive enough to accrete gas, then we have a totally different scenario, and we can have different scenarios in general. The planet can be either a puffy super Earth, or it can be a mini Neptune here, as you see on the very top of the graph, or it can lose the atmosphere. So we end up again with a terrestrial-like planet. If the planet continues to accrete material, then the protoplanet will be Neptune type, as you have on the very bottom of the graph, which is a hot Neptune. And if during its life it loses this gas that will accrete in the meantime, it will end up as mini Neptune again, or super Earth, this type of planet, or as a Neptune-like planet that we have in our solar system again, and we know it. And finally, if the planet becomes very massive to start accreting even more gas, there is no way to stop it, and there is no way to lose this gas. So in that case, it will be a Jupiter-like planet, as you see on the top. And the limit for this type of planets is 13 Jupiter masses. This is very brief. We know that it's very complicated, but only by starting seeing these atmospheres we really know and start understanding the paths of these planets, how they ended up like this or in different scenarios. For some cases, we have Jupiter-type planets, which are formed far away from their stars, but after interaction with the protoplanetary disk, they end up very close to the stars, so the hot Jupiters. With ARIEL studies, we can start seeing and understanding where in the protoplanetary disk these planets were formed and follow their path back to history. Now about the methods of ARIEL. One method that ARIEL will use is transit spectroscopy. So in that case, we wait for the planet to pass in front of the star, and we observe it spectroscopically. That means we observe in different wavelengths, in different colors. When we observe and we measure the size of the planet in the different wavelengths, it will have a variation. So it will have bigger or smaller size on the different wavelengths. Of course, it's not that the size of the planet is changing. This is because of absorption of different molecules. And on this graph, we have an example. As you see, on 1.5 micrometers, the planet looks much bigger compared to 0.7 micrometers, where the planet looks much smaller. And this is because of strong absorption of water, as you see. And you can think of the same process at different wavelengths and different, of course, molecules. The second method is Eclipse spectroscopy, again, important method. So in the case of the transit spectroscopy, we observe both planet and star. But in the case of eclipse spectroscopy, we wait for the star alone itself. So the planet goes behind the star in order to gain the spectrum of the star, and then subtract that from the combined spectrum, because what we really want to see is the planet spectrum itself. Of course, this is much more challenging because the planet spectrum will be very small. So I think it's around 100,000 smaller. It's incredible, but still it's quite important because we can gain some information about the structure of the atmosphere and some other important molecules. This is an example of spectrum, and in the specific case is the Earth's spectrum. Quite interesting to notice is that there are two spikes in carbon dioxide and ozone, as you see, and this is due to the Earth's stratosphere. So another important thing that we can see in and observe in atmospheres of exoplanets. Now, as we said, ARIEL will observe 1,000 exoplanet atmospheres. And as you understand, a transit is a phenomenon that happens at specific time. So in that case, time is very critical, and ARIEL will observe one planet after the other, as you see an example here. And it's quite important because we don't really want to miss the transit or gain half of it, because in that case we get less information, or even important information, we lose it. Especially if we don't want to end up in situations like this where we have half of the transit, so we miss information. And this is exactly where ground-based observations can become very important, either with small or bigger telescopes, and preparing the most efficient way this mission. And I will give you an example of an exoplanet that is a target for ARIEL, and we also observed it 2 years ago. So this planet is WASP-83b. It was firstly discovered in 2012, and this was the only observation as well, because most of these planets, after their discovery date, have not been followed up. And we expected an uncertainty of plus minus 9 minutes in the transit. So when we observed it, we found a shift of 25 minutes, which is quite a lot. And we re-observed this to confirm it. Now, if we extrapolate this to the ARIEL time when ARIEL will fly, the ARIEL observation will be shifted by an hour. So, as we said, missing information about the transit. And in order to better organize this effort, and of course, prepare in the best way, in most efficient way, we initiated the project ExoClock. And if you think about it, it's 1,000 planets. And it's not that bad because that requires 1 per 2 observations per year for each planet. But it's something that definitely needs to be well organized. At the same time, we believe that a space mission, as in general, science and research is a collaborative effort, and it should include as many people as possible that are interested in that. It's at the same time a way for someone that wants to contribute to the mission. And we strongly believe that every transit is a unique opportunity to contribute, even if it's one transit, even if it's one observation. And of course, all these observations can become available for further research apart from ARIEL. So it's a really open project, collaborative effort, which includes both professional and amateur astronomers. We have created a dedicated website for ExoClock, which at the same time is a service. So it will provide the ephemeridess of these planets apart from everything else. So the users, and Mark is very aware, aware of this, he's using already our platform. The users that are interested can just go to exoclock.space, register their telescope and their location, and then a personalized schedule will be there for you for every single night. So this schedule is based always on your equipment and your location. And also you will notice that the planets, as in this case, are marked with some priorities. So we have a medium, higher or lower priority, and that is really depending on how significant is the observation to be done or how difficult, for example. And it's really important to have the prioritization system because everyone has different equipment and different, is observing from a different location. So it's a very efficient way to distribute the targets among the community. And finally, when you observe your planet, you upload the observation after having analyzing it, and you will get, we will do the validation of the observation always based on the literature, but also on any observed inconsistencies with other observations. The fitting is also done in the system for consistency reasons. And then the final result will be a light curve that is published in the website, but also in publications. And at the moment, we are preparing the first publication. So as you see, this is by Mark, who is quite active. And apart from credits to the observers, this result contains also technical information, as for example, the equipment or the different the date or exposure time, for example, but also scientific details. So in that case, you can also see the predicted time and the comparison with the observed time of this result. And also remember that we will use all these observations to better refine or update the ephemeris for each of these planets. And this is an open call to anyone that is interested and would like to join a space mission in this way. The ExoClock project is really open. You can register at ExoClock directly. It's very easy. And if you don't have any experience in exoplanets, but you have a telescope and a camera, and you would like to try it, or even to learn about it, we have created a separate website, which is ExoWorld Spice. And ExoWorld Spice is a really dedicated platform for educational purposes. Of course, this is a process where we want to interact with each other. So we send feedback to users to improve their light curves. And we also send newsletters every month with educational material and any news on the project, but also on the mission. And we try to maintain as much as possible the interaction, because it's what we think as well is important. It's always a community and a collaborative effort. A few words about ExoWorld Spice, which is the website www.exoworldspice.com, and as is on the previous slide. So what you find in ExoWorld Spice is all the details that you need to observe an exoplanet transit. So you will find how to observe, all the guidelines and audiovisual material on that, but also details on how to analyze your data. And we understand that the analysis part is many times quite important, or a problem for especially amateur astronomers, where they struggle. So for this reason, we have created dedicated software, which is HOPS. And this is actually the result of many years interaction with both professional and amateur astronomers, in order to make it as user-friendly as possible and fast. And this is also available on the website. You can download it. You can find all the different guidelines on that. And it's compatible with operational systems. It's quite easy. And of course, if you don't have experience or you don't have equipment, and this is really appreciated, we have in our website 26 available observations at the moment, which are kindly provided by some of the partners, but also ourselves, where we conducted these observations. And you can access this, download the software, download one of the datasets, start training, or even see if you like it or not, and then start doing your own observations if you have equipment. So to pretty much wrap up at the moment and leave more time for questions and more interaction, again, I would like to say that everyone is welcome, and we believe that every observation is important and can count and be part of this mission. And every observation is unique, of course. So register at ExoClock and get your own schedule and see how the different targets, and start exploring more the exoplanet science. And if you don't have any experience at all with the topic, you can also join ExoWorld Spice. And at that stage, I would like to share my own perspective on the topic. And after my exoplanet involvement. So exoplanet is a fascinating, the exoplanet field is a fascinating field, and it's really something that can teach us and give us information more about the universe, and we can expand our horizons beyond our solar system. And at the same time, it's really a field that can give us more information about our origins and really start seeing the Earth in comparison with these planets, and just see how different it is or how similar. And here I have a collection of different, some of my favorite images of the Earth. And I would like to thank you and have any questions and discussion with you.
Well, thank you very much, Anastasia. Mark, just for clarity, would it be useful to just very quickly tell people what you actually did to achieve that result that you got?
Yes, okay. You need a fairly long, clear window at night, because the transit might be something like 2 hours long, and you need to be able to observe it for about an hour beforehand and an hour afterwards. But basically, it's very like doing normal astro imaging that we do in the imaging group in the society. You've got to work out what the exposure is, which, as we discussed the other night, is quite important, so that the star you're following, you're trying to track the exoplanet for, you've got to make sure it doesn't saturate your sensor. So you've got to get the exposure just right. But once you've got that right, basically you take as many exposures over that 4 or 5 hour period and download those and then run them through this very, very nice piece of software, actually. And that is really what it comes down to. It's a long session. I've had lots of sleepless nights doing it, but you download the data. And HOPS really is a very nice piece to use. It's by far the easiest piece of exoplanet software I've ever used. And what comes out of it is a very nice graph at the end, and you can see how your observation compares with the predicted one, and it's quite nice when you come up with something different. So it's very satisfying, yeah.
Great, Phil, thanks for
Very
that.
good.
Okay, Peter.
We have a few questions. There's a couple that can probably be linked together. Mark asked a question: how does ARIEL mission compare with CHEOPS?
Oh,
May I take this?
of course.
Okay, so ARIEL will be doing a spectroscopy. So we'll have it will have a spectrograph to resolve the light at different wavelengths, while CHEOPS is doing photometry at different filters. So this is the fundamental difference, but without the spectrum, and of course ARIEL will go to further infrared, so up to around 5 microns. So around 8 microns. So it is the infrared, and what is the most important thing, because there the signatures of the different molecules are strong. So it's spectroscopy and wavelength coverage. So they are two completely different missions. CHEOPS will, well, the only thing we have in common at the moment is that the CHEOPS is also observing known exoplanets to further characterize them. But the focus of this characterization is on the on updates of their characteristics, like the size and the timing. So we get very precise measurements of the sizes of the planets, which is still one problem. And without having that precise information, with this precise information, we will be in a better position to decide about the future targets also for ARIEL.
Thank you. There's a question from Sean. Sean, would you like to unmute yourself and ask your question? No? Oh, well, we'll move on. There was a YouTube question from Carmelo Falco. For the ARIEL mission, was the target exoplanets, were they selected yet? What are they and will they be?
Well, the answer is no, because many of the targets that ARIEL will observe have not been found yet. It will, so ARIEL will fly in 2028. So we will have many more planets by then. TESS is already finding quite many. So we are selecting some of the current ones, but a very large portion of them will be discovered later. So it is something that is ongoing.
Right.
We don't have any fixed targets. It's too early for this.
Part of the question was, what will be the selection criteria for selecting these planets?
Well, you can imagine that the bigger the atmosphere, the better the signal that we can get for the planet. So we are looking for, we take into account the mass and the radius of the planet. You can imagine that a planet with a big radius and a small mass will be a better target, because we expect it to be more puffy, so have an atmosphere around it. So this is what we are going after. But ARIEL will first do a survey. So we will look at 1,000 planets very quickly to see which ones are good candidates, and then we'll focus on 500 of them.
Very good, thank you. There was a question from Mike and Carl and Neil, which is basically a very similar question. After the launch in 2028, how long before you get good data and usable data?
Oh, a few months.
Just a few months?
Mhm.
Very good. Andrew, the president. What is the basic equipment required?
So I asked a question before I asked Mark to outline what he did. So he neatly, I think, summarised that if you've got a camera and a telescope, you stand a good chance of being able to take part, and the time, and where we live, the weather window.
Absolutely. So actually, we have tried even with, some people have tried with 6 inches telescope, but from our experience, we did very nice observations with 8-inch telescope. So a simple CCD camera and that 8-inch telescope is enough. But of course, we have the moment telescopes, which are much bigger, and have to 1-2 meters or even more. It doesn't really, it's not a problem or a limit. What we really try to do in the project is distribute the different targets, because as we said, an 8-inch telescope will be capable of doing specific observations compared to a 16 inches, where we have even more difficult targets. So absolutely everyone that has an equipment that starts from 6 to 8 inches, but of course we can try some things under research if you can still do a very useful observation with 6-inch or lower. So
very good. I think that sort of answers Mike and Carol's other question as well. There's a couple from YouTube from John Morrell. Is there a risk that the current periods for the exoplanets is a multiple of the true period, and thus we should check at 1/2 and 1/3 of the period? I think I understand that question.
Very good question. But usually when exoplanets are discovered, very long baseline observations are done. So the exoplanets are being monitored continuously for a long time. So if you do RV, for example, or just a periodogram, so this may give you some false positives at the different periods, but usually we do continuous monitoring. So there is no way to miss a transit in between.
Right.
But it was a very good question.
Sorry, it was another one from John Morrell. Will the photometry from Gaia help with confirming the transit times? Or are these stars too bright for Gaia?
Well, Gaia, I'm not very aware of this, but I don't believe that Gaia is doing enough long observations long enough for us to have a lot of useful information. So current photometric follow-up from space, the main source will be Cheops and the extended mission of TESS. So Gaia is not going back to the target so often for us to have many useful light curves. So we will not focus on that.
Okay, there's another one from Mike and Carol. Do you want to ask your question, Mike?
Anastasia mentioned that a CCD camera could be used to take the images. Would a DSLR camera work just as well? Because that's all I've got.
So personally, I haven't used a DSLR camera for an exoplanet transit. I didn't have the chance, to be honest. But I know that there are people that have done that. So it's going to be a good experiment, I believe, to see if you can catch some of these planets, especially the easiest targets. So if you are interested, you can give it a try, and we will be there to assist you if there are any questions for you.
I have the impression that someone has already uploaded on ExoClock an observation with DSLR, but I'm not sure. But I think I saw something like a camera DSLR at some point, and I was quite surprised.
We can definitely check and see, but it's something that can be done, yes. We know that some people are doing it.
Okay, thanks.
Very good. Any more questions on the team? We've got a good turnout tonight. So
Sean, you want to ask yours?
Sorry, Andrew, were you talking to me?
Sorry, Sean. Peter said you had a question.
Oh, yes, actually, it was firstly wonderful presentation. Thank you very much. It was really around using the data you've been collecting from studying so many exoplanets in terms of modeling the structure of our own solar system, particularly in understanding what lies out beyond Neptune and maybe various categories of planets that might be orbiting the sun that we simply haven't found yet.
Very good question. So one, well, this requires some discussion and thinking, but to my view, the more we understand about exoplanetary systems, the more we will understand also our own solar system. Probably the question is more oriented towards the structure of the systems. So maybe data that we already have by the distribution and orbit of exoplanets is giving us some information about this. But as you saw in Anastasia's talk, with the atmosphere, we will have this chance to maybe have a look on like where the planet started and how it migrated inwards, because there are many planets that have done so, and we know this is happening often. So this will be our first try, for example, to try and quantify this. We know very little. We're just speculating, or we're doing models about how solar systems evolve. Our knowledge is quite limited, and it's not my field of research as well, so I don't know much more. But the problem about Neptune, so the second part of the question, is that as far as exoplanets are concerned, Neptune is extremely far away from the sun, and such exoplanets will not be within our reach for quite many years, I think, in the future, because they're so far from the stars, and the chance of us finding them is very low.
So we won't get a
Very
clue to
much.
Planet 9 then.
Very, 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 very difficult. I would say unlikely. Unlikely.
Andrew?
Okay, well, thank you very much for a very interesting and enjoyable talk. Hopefully, you'll have a few people who want to try, certainly within our society. I believe there may be some people watching on YouTube from some of the other societies, and we'll try and spread the word as widely as we can. And one of the benefits of putting this on YouTube is we can refer back to it if anybody expresses an interest. Shall we move on to our slides now? So again, thank you very much.
Thank you very much, everyone, and we're welcoming you in the team if you're interested. Thank you again, Mark, for the invitation.
Thank you very much.
We can probably say that we have at the moment around 100 users, and 80% of them are amateurs. So we get a lot of support by amateurs, which is very important for us to connect with the amateur communities.
Yes,
I would say, I think ourselves also started as amateurs before going into working on that.
And actually, this is one part of our mission as well, to open science, planetary and astronomical science as much as possible, and that's why we created all these tools. So you are welcome to join and use all this material. Thank you.
Excellent. Thank you very much indeed.
Thank you.
Thank you.
We did also publish this on the Royal Observatory Edinburgh site. So again, you get some more, hopefully some more interest, people referring back to that site and onto the YouTube. So probably some post-presentation engagements will come up.
Absolutely. Thank you.
Thank you. And just before we close, we've put together a fairly frequent set of meetings, much more than our normal once a month, to keep people interested in astronomy and feeding their appetite during this lockdown period. And just a reminder that on the Tuesday the 21st, we can join the Royal Observatory talks. On the following Wednesday, there's our Astro Imaging Part 3. Parts 1 and 2 are available on YouTube. And on Friday, Peter will be talking about remote robotic imaging. So for those who can't get in the garden, you can buy some time on a big telescope and do some work. Tosh, ever the mysterious, will be doing something else as well as astronomy and space news. And then we have what would have been our regular monthly meeting on Friday, the 1st of May. All that information is available on our website, as will be the links to all the YouTube's videos. So thank you very much, everybody. Thank you very much to the speakers. Thank you very much, Mark. And if you want to keep in touch, not only is the website there, we've got Facebook and our Twitter account. And so that's, thank you very much and good night from me. Thank you.